Hello, this is Dr. Asan Abdullah with the course Complexity and Analysis of Algorithms. The topic which we are covering is graph algorithms, and the subtopic is single source, shortest path. And you will understand what is meant by this when we go through the course. The supplemental website for this course is easymcq.com/goget. And these are the course content. So you see that we are right now at topic number 5, which is graph algorithms. A few words about the supplemental website, which basically is a learning management system, and it has many features, wonderful features, which will help you in understanding and facilitating and getting the most out of this course. And these features are covered in these 6 videos, which are available on the course website. So I would suggest that you look at those videos. Now we move on to the learning management system. So we read the learning management system and all those wonderful features, what is meant by level, and everything has been explained in those 6 videos I mentioned. There are core computer science courses, then there are hard courses like natural language processing, artificial intelligence, machine learning, and so on. But we move to the course of our interest, which is analysis of algorithms, and we move to the topic of our interest, which is graph algorithms. Okay, and these questions, question number 1 to 5, and then up to question number 10, question and answer, they have been covered in video 5A. So now we move to video 5B for graph algorithms. The course is analysis of algorithms. So up till now, the content which has been covered, including what you see on the screen, is this number. Okay, so what is a single source shortest path problem for weighted and unweighted graph? So graph can be weighted and can be unweighted. So single source shortest path problem definition we will cover in this question and answer. And we will cover this problem for the unweighted graph and also for the weighted graph. Unweighted graph have either the edge is present or the edge is missing. In weighted graph, that may be the same case, but every edge has a weight also. Non-negative weights we are looking at right now. And then we will look at the algorithms for unweighted graphs and for weighted graphs and look at the time and space complexity. So this is the reading time as per the text, 1 minute and 29 seconds. Of course, there could be diagram also. So let's look at the description of this question, the answer of the description. So what the problem is? The problem is finding the shortest path from a given source to all other vertices. Okay, so let me highlight this. So from given source to all other vertices in the graph, single source shortest path. So the what is meant by shortest path? The path with the minimum cost, because this is all the number of edges. The minimum cost is when it's weighted, and if it's unweighted, then it is the number of edges. And this problem is applied, has application in different areas such as routing, so network optimization, navigation, and the list goes on. So for the unweighted graph, okay, when all the edges have same weight, we assume it to be 1. And when the edge is present, of course, and when the edge is not present, we assume the cost to be infinite. So what is the task? Is minimizing the number of edges traversed between the source and the other vertices. Okay. So what is the primary goal? Finding the fewest number of edges. That is for unweighted graph. For weighted graph, each edge has an associated weight or cost. The shortest path is not the number of edges, but minimizing the total sum of edge weights. Okay. So it is not that. So this is a more complex problem. The goal is to choose paths that minimize the total weight. Let me clean this and we move ahead. Okay. So what we do is, so the algorithm for unweighted graph is breadth first search. Towards the end of this topic, we'll spend more time on breadth first search. So explore the graph level by level, and if you go towards the end of this topic, you'll find animation also for breadth first search. Okay, so let's first see how the objective is to find a route from vertex 0 from here, start from here and end here. Okay, and we write a program to find this route. Now using a naive approach may not result in something very efficient. Say for example, because this is one possible route. This is of course not the optimum route. Okay, so and this is an unweighted graph, so the cost of the path is the number of edges. So 1 2 3 4 5, obviously this is not optimum. How can I say that? Because I can look at it. This is very trivial case. I can do by inspection, but when we have like 10,000 vertices and I don't know, like 50,000 edges, then it's not so trivial. Okay, now let's do breadth first search. So I change the color. Okay, so the breadth first search moves level by level. So breadth first search is the last subtopic which is covered in this topic of graph algorithms. So we do a breadth first search. So this is the first level. Okay, this is the first level, and this is the first level, still going to first level, right? And then from here we go to the second level. So the second level could be this one, and it could be other one also. All right. So that's, so say for example this is the second level. Okay, this is the second level, and this is the second level. All right. And then we have the third level. So the third level, this will not be the third level because that will create a cycle. This can be a third level. Okay, this can be the third level, and this will not be because this will create a cycle. So we see that we are this breadth first search is able to find the path from this vertex to the ending vertex of path length 3. But the naive approach took more time, and it of course it has a longer path. So the path what we got is 0145. 0145. This is the one we got, and of course other paths are also possible. So if you are interested, there are a lot of material to read and a lot of material to go through. Okay. So show the working of single source shortest path search for given unweighted graph. So there have to be input parameters. The parameters will tell the system or the application from where to start and where to go, and then it length of the shortest path, choosing the closest node, and then performing the best first search. All right. So the input parameters are identified. Let me highlight them. All right. So the input parameters are highlighted. Find the shortest path from S to all other vertices. So S is the starting vertex, and we are interested in the number of edges. Why? Because the graph is unweighted. So there are no weights on the edges. This is clearly a special case of the weighted shortest path problem. Special case meaning that the edge weights are all identical, one, or they're infinite, missing edge. So learn the shortest path. Keeping track of the actual paths will turn out to be a matter of simple bookkeeping. Just recording the stuff. So choosing the closest node. Suppose we choose to be that is VV3. Okay, and then from we go from S to V3, and then the path of length 0. We uh, we can then mark this information and keep on moving. So the breadth first search operates. So we continue with the single source shortest path problem. And this is a slightly more involved example as compared to the simple example we did earlier, because that earlier example was for undirected graph. This is for a directed graph and with slightly more edges. So let me zoom this image for you so that it becomes easy to comprehend. So we start with the vertex V3, okay, and the cost of vertex V3 being visited by V3 is 0. So we have the 0 here, all right. We have the 0 here, and then we perform the breadth first search. From V3 we can go to the first level of search, which is V1, all right, which is V1, and which is V6. This is the first level of search, and let's move ahead. So from V1 we can either go to V2, which is the second level of search, or we can also go to V4, which is the second level of search. So put a 2 here. At both places put a 2, and from V6, which doesn't have any out degree, cannot go any further. So now we move out to this figure number D, and now from V4 we can go to the next or the third level, which is V5, vertex V5, and uh, and of course from V4 we can also go to V7, which is vertex at a level of 3, like this. We can pick actually both of them, because since it's a directed graph, and you can observe that the cycle is not possible here. So you can see that using breadth first search, we were able to perform the single source shortest path problem effectively. Okay. So now let's move on to, let me clear it and we move on to the next question. Key single source shortest path problem. What are the key algorithms for weighted graphs? Now that was for unweighted graph. Now let's look for weighted graphs. So for weighted graphs, we have, these are the classical algorithms. The classical algorithm is the Dijkstra's algorithm, and this is used extensively in real life applications because of its nice time complexity. So we will very briefly cover the Dijkstra's algorithm in this question and answer, but of course there's a complete example of Dijkstra algorithm also. Then is the Bellman-Ford algorithm and the Floyd-Warshall algorithm. So I will tell you in within this question and answer their use cases, their time complexity. This is the fastest one among all these three. And then the steps, the issue with Dijkstra's algorithm, which I will talk very shortly. So so we are looking at weighted graphs. Okay, we are looking at weighted graphs. Let me, all right. So we are looking at weighted graphs, associated weight. There is the each edge has associated weight. So Dijkstra's algorithm application for graphs with non-negative weights. So this is the, you can call the limitation or the condition of Dijkstra algorithm, that the weights of the edges should be non-negative. And the time complexity, I'll go into details. That this is the time complexity. Okay, when you achieve this time complexity, when the priority queue is used and it's implemented as a binary heap. So of course it can be further optimized using Fibonacci heaps. So you can see that over here, this log of v is not multiplied by e. So this is the slower version, this is the faster version, if you look carefully. So how does it works? Extract the vertex u with the minimum distance. From where you start, go to the closest one, and for each vertex adjacent, each vertex v of u. So from u you go to the, and from then on what you do is, for each adjacent vertex v of whatever vertex is adjacent to u, if the distance to v through u is there is an alternate path, okay, within the explored space, then you update it and decrease the priority of u in the priority queue, because then it's closer. Okay. So how do you go about initialize the distance to the source vertex as 0 and all other vertices as infinity which have not been explored or discovered, and insert all the vertices in a queue based upon their distance value. So this is the sorting part. This sorting part is covered with of the log of v thing. Okay, and till this priority queue is not empty, keep on doing this. I'll go into more detail of the Dijkstra algorithm. So what is the Bellman-Ford algorithm? Applicable for graphs with negative weights. Okay. So the limitation of Dijkstra algorithm was that it does not works with negative weights, number one. So Bellman-Ford algorithm, these two gentlemen, Bellman and Ford algorithm, it works with negative weights and can also detect negative weight cycles, because the problem with Dijkstra algorithm is that when there's a negative weight, and as so it will get kind of stuck into that cycle, because in every loop or every iteration or every visit of that negative weight cycle, the cost will go down because the number is being deducted. So basically the Bellman Ford algorithm detects the negative weight cycle and works with negative weights. So how does it work? If the distance to v through u is less than the current distance, okay, update the distance of v, right? Similar to Dijkstra, if the distance to v through u is less than the current distance to v, a negative weight cycle exists. Okay, so that is the thing. So less than what was finalized, right? Kind of, and then again there is the distance goes down, again it goes down. So there's a negative cycle, and you need to then initialize the distances, okay, and then of course repeat v minus 1 times and check for negative weight cycles, because if the negative weight cycles are not checked, it will go into kind of an infinite loop. So that is the Floyd-Bellman-Ford algorithm. Now let's look at the Floyd-Warshall algorithm briefly, because the more focus is towards the Dijkstra algorithm, which is used extensively. So this algorithm, all pairs of shortest path, right? So basically, if you look at all pairs, so if you have v vertices, so we are looking at v into v minus 1. Okay, or let me use the other pen. So basically, we are looking at what? We are looking at v into v minus 1, okay, divided by 2. So that is the two pairs. These are two pairs, right? So this finds the Floyd-Warshall finds all the distance between all the pairs. This itself is order v square. So the time complexity of the overall algorithm is order v cube. It's very slow. So basically, for each pair of vertices ij, which are order n square, update the distance matrix to the minimum current distance, right? And initialize the distance matrix and so on. So what is our concern is this order v cube. So compare the time complexities and applications of Dijkstra algorithm, Bellman, Ford, and Floyd-Warshall's algorithm. So look at the time complexities. So we see that the time complexity of Dijkstra's algorithm is or you can read it, okay? So see that this log of v gets multiplied by the sum. This is the product itself. So this is fairly slow. This could become, I'm stressing on the word could, become v cube, because e can be v square. It could, but this Floyd-Warshall is already v cube, so this is already very slow. So this is the fastest one, this is the next slower one, and this is the slowest one. And the fastest is this one, and the slowest is this one. So let's look at some more Dijkstra algorithm is more efficient and it is commonly used in real world applications. Why? Because it tends to perform better. And the other benefit of Dijkstra algorithm is, let me highlight that benefit. The other benefit is that it works where E is not too large, sparse graphs related to V. Because in real life problems, the graphs are of course there. There are lots and lots of graphs in real life, but their density is low. So there are fewer edges, right? So the fewer edges. So this almost goes to like order V log V. It's just about sorting itself. That's it. And Bellman-Ford's algorithm, when the edges are large, okay, and of course works with negative weights also. But it is because this time complexity, it is not desirable in most practical scenarios. And when the graph is dense, then it's a disaster because the E becomes a V square. And Floyd-Warshall algorithm is the slowest, okay, because it grows cubically with the number of vertices and so on. So these are some of the limitations and comparison of these algorithms. So let's look at the working of the Dijkstra algorithm for a given weighted graph. Okay, now we are at the last question and answer on single source shortest path algorithms. So let's look at the working of the Dijkstra algorithm for a given weighted graph. So there is a source vertex and then we calculate the shortest distance. There is one criteria in that shortest distance which I will share with you, and the weights have to be positive, otherwise that criteria does not work, and that is the limitation of the Dijkstra algorithm. So what is the criteria which I mentioned? So we start with the source vertex. This is the criteria. The algorithm assumes that the weights are all positive. Okay. Because why this is assumed? Because the distance from x to y to z is always greater than the distance from x to y. So that is the underlying assumption. First is the positive weights, and based upon that assumption, the distance from x to y to z is always greater than the distance from x to y. Okay, this has to be true because, but if the graph has negative or zero weights, then Dijkstra algorithm cannot be used. Okay, so let's look at the working of the Dijkstra algorithm through this example. So let me zoom in. All right. So this is the scenario we have, that we have the starting vertex. So this is the starting vertex is A. Starting vertex is A, and this is the VIS is the vertex visited. Okay, so when a vertex is visited, this is set to 1, and the distance since the vertex has not been visited, so the distance between that vertex from the previous vertex through which the vertex was reached is infinity. So since nothing has started, so this is set, it is like, it is not valid. So let's start from here. So we start from vertex A. We start from here, and from A we can, through A we can visit vertex E. Okay, and through A we can visit vertex B. So from through A we can go to B, and through A we can go to E also. Now the cost of going from, now since now you see that it visited has not been set to 1, because we will the algorithm will ensure that the distance cannot be further reduced, then it will be set to 1. Okay, of course now it is set to, it's not infinity because these vertices have been explored but not visited yet. So and of course C and D are not, and of course E is A is like self loops are not allowed. So from this will always remain the same. So this row will always, because that's the starting vertex. Now we move on to step number 2. Now the step number 2 is that once we have when we can go from A to B, and we can go from A to E. So what are the costs involved, what are the distances involved? So this is basically a greedy algorithm with basically, and uses dynamic programming bookkeeping. So we see that the nearest vertex is E. So from A we can visit from A we can visit E, and since we have visited E, so we set this to 1, and the cost of that edge weight is 1, so this is set to 1. All right, so this is the, in red is the vertices and the edges which have been included, and from E we can reach D with the cost of from E we can reach D because the single source shortest path. So and the cost is 1 plus 7 8, that has not been selected yet. And then from through E we can also reach C, and the cost from A to, because single source shortest path, the cost is 3. And through B we can reach C also, and the cost is, from A we can go to the cost, and from A we can reach B also. Okay, so that is the cost is 7. So based upon this, we go to the nearest one, and the nearest one reachable is C. So from A we go to E, and from E we go to C, and the cost is 3. So this is set to 1. This is set to 1. This will always remain the same. Okay. And the red is in the part of the graph which has been fixed and visited. All right. So now we have explored these vertices C and E, and from these vertices, where can we go? So we see that from through C we can reach B. Of course, we can reach B also through A, but the cost is more. So the cost of reaching B through C and the cost of reaching C is through E. And so the cost is 1 plus 2 plus 3, the cost is set to 6. And so it is set to 1 also. This was already done, this was already done. Then we keep on repeating this process. And ultimately, we end up with the minimum a single source shortest path solution. And that is the solution here. This is how Dijkstra algorithm work in a very simplistic form, but it is very effective, and it is used extensively. So this is all we have for this topic, basically subtopic of single source shortest path. Thank you very much.